In the first part of this week, we'll concentrate on solving the Laplace equation. The Laplace equation is one of those fundamental partial differential equations that shows up in a lot of places. For instance, in fluid dynamics, in electricity and magnetism. It's a very good sample equation to learn the methods of the finite difference approximation for solving PDEs. This is a boundary value problem. We're trying to find the value of phi everywhere on a grid, given its boundary conditions. So to solve such an equation, first we have to construct a grid. So let me draw some type of rectangular grid, like so. So this will be the domain of solution. Let's say this is x, and this way is y. What the goal of solving the Laplace equation is to find its value at these grid points here. These are the interior grid points. And we want to find the value of phi at those points. And we're given the value of phi on the boundaries. So this would be the boundary value, say, out here. Okay, so that would typically be given. So what we need to do is to construct the equations for phi on the interior grid points. We have some domain typically, so this could be, say, some Lx value. This one could be some Ly value. And then we have some grid spacing. This could be, say, delta x. This could be, say, delta y. Okay? We're going to do a simplification. We're going to have delta x equal to delta y. We're going to have Lx equals Ly equals 1. But we can construct some sort of general problem at in the beginning. So we have grid points, grid in x, grid in y. We can define x sub I then equal to I minus 1 times delta x. And then I can go from 1 to little nx grid points. We can define the y position on the grid by y sub j equals j minus 1 times delta y. And j then can go from 1 to n sub y. Okay? So this is through these values. Okay. The main task in this video is to discretize the Laplace equation, which means to write the derivatives in a form that gives us the value of phi on the grid. So we're going to define then phi at the xi, yj grid point by phi sub I comma j. And we'll be looking for an equation for phi sub I comma j. So we need to consider how to convert these derivatives. Let me draw a picture with 3 columns and three vertical lines, 3 horizontal lines. This central point here is going to be our phi ij. So this will be the x-axis. This is the I value. This is the j value. So this will be I plus 1, I minus 1. This will be j plus 1, j minus 1. Okay? We want to then convert this derivatives. So we have our central finite difference approximation for the derivative. if we're taking the derivative with respect to x, we have d squared phi dx squared. We want to approximate that using our central difference formula. And the derivative in x means we need this point and this point. And if we use our derived central difference formula, then this becomes phi of, let's start from the right. So I plus 1 comma j minus 2 times phi of I comma j, twice the middle point, plus phi at I minus 1 comma j divided by our delta x squared. And this is the value of the second derivative at the ij grid point. So the second derivative of phi at this middle point using the central difference approximation will be its value here minus twice the value at the middle plus the value on the left divided by delta x squared. That's why we derived the central difference approximation in the last video. We can do the same thing with y. So d squared phi dy squared at the ij grid point. Right? Here we'll need this point here and the point underneath here. So I is fixed here. So we have phi sub I of j plus 1 minus 2 phi I j plus phi I j minus 1 divided by delta y squared. Okay? The central difference approximation in the y direction. Okay? Put it all together. We're going to simplify. So we're just going to take delta x equal to delta y. There's no point in making this complicated. We might as well use a square grid here. Then we have the sum of these two equals 0. We can multiply through by delta x squared and clear the denominator. We can multiply also through by minus 1, as is the tradition. And the minus 2 plus minus 2 is minus 4. And we multiply by minus 1. That will become 4. So the sum of these two equations will become 4 times phi ij. And then we have minus phi I plus 1 j minus phi I minus 1 j minus phi of I j plus 1 minus phi of I j minus 1 equals 0. Okay? This is called the discrete Laplace equation. This is the discrete Laplace equation. So by gridding up our domain and using the central difference approximations, we can convert a partial differential equation, the Laplace equation, into a difference equation, the discrete Laplace equation. The goal then is to solve this for phi values that are interior to the domain given the phi values on the boundaries. We still have a lot of work to do, and we'll do that in the next few videos. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.